Hello, I'm Ivan, and today we will go through the notebook with examples of how you can write and use code to apply uncertainty techniques on your tasks. In this notebook, we will firstly go through uncertainty and deep ensembles for classification tasks. Then we will see how you can change it for regression, and lastly I'll show you how you can apply prior networks for your work. Let's start. Let's recap why we use ensembles in uncertainty estimation. So assume that we have a range of models, an ensemble, where each model is probabilistic and it predicts targets based on features and some weights. And weights, they came from weights of the network. They came from some distribution over weights conditioned on dataset, on our training dataset. So this distribution depends on some dataset, task, optimization procedure, and model architecture. In deep ensembles, we train each model with a different random state. Thus, we obtain a range of different models, and also there are research papers that show that these networks are usually end up in different local optimas for the same task, and thus they are quite different. So they each of them has its own view on the task and the solution. We should also know what is entropy to work with uncertainty estimation, and I'll remind you that entropy for discrete distribution for classification task is simply minus some pi multiplied by logarithm of pi, where I means class ID for some prediction. As you know, through ensemble we can calculate total uncertainty, which is entropy of expected answer over the ensemble, which is in a simple case of our classification ensembles, entropy of the mean probability prediction over the ensemble. We take ensemble and we just average probability predictions from each model for each input. Expected data or aleatoric uncertainty looks like this. This is expectation over our ensemble over some distribution of weights of entropy of each model. So in classification it is also simple. We calculate average entropy over our ensemble. So each ensemble gives us some probability distribution over output classes. We calculate entropy of this distribution, and then we average this entropy over all models in our ensemble. And knowledge or epistemic uncertainty is also simple. It is the difference between our total uncertainty and expected data uncertainty. So the difference between entropy of expected and expected entropy. Let's also recap how it looks like visually. We can consider three classes classification and visualize our models predictions in on a simplex. So here each corner means some class, and the closer model prediction to the corner means the higher probability of this class. And you can see that each dot here, each point, means some prediction of some model in the ensemble, and the whole range of points is the whole ensemble. And you can see if the prediction is confident, then all models predict similar corner of our triangular. If we have high data uncertainty, then each model is not confident about the prediction, so the distribution of probabilities over classes looks like uniform, more or less uniform distribution. So each model gives equal probability for each class. And here we have knowledge uncertainty case, where our models are distributed uniformly over simplex, so the predictions are totally random. This means that the models and the whole ensemble, they haven't got information about this input, and they don't know what to do, and they do some random stuff. There are different ways to generate ensembles. You can make them like we do in this work via different random initializations. You can do them through dropout or some sampling or some checkpoints, but the best ensembles, the best technique to generate ensembles is the simplest technique also, to choose different random inits and train your models with different random inits and obtain an ensemble. More information about different ways to generate ensembles you can find in our video about ensemble generation. Yeah, we will use the simplest and yet the most effective way to generate them. For simplicity, I'll show you concepts on easy tasks where you can train your model fast and play with it. And you can find high-scale experiments in scientific papers introduced in our tract, as mostly they have their GitHub repositories, and you can find code and results here, and results in these repos. Okay, let's start. I'll show you how it is to use uncertainty estimation techniques in your code. We will use PyTorch and some default and some usual Python libraries. For classification, I'll use Mani's dataset as I think one of the most simplest datasets you can choose. Here we set some settings for our experiments and load data with the Torch data loaders. And dataset looks like that. You have some small images with numbers inside these images, and you have classes. And based on image, you should classify it classify it with digits from 0 to 9. We will use simple network here with 2 convolutional layers and 2 linear layers. And we will use simple softmax to predict probabilities. And here we will use log softmax because it is more stable to calculate something. So if we want to obtain probabilities afterwards, then we should make forward pass of this network and then apply exponent on the output, and then we will have probability distribution. We will use cross entropy loss. Here we create our ensemble and train networks in it. Yes, that's how we will predict our probabilities. We just take predictions and apply exponent function. Let's go through this function called predict uncertainties. Here we have a list of probabilities for our predictions. For some images we put inside. We put in this function. We accumulate all probabilities in this list, and then we can calculate the expected probability. This is the average probability of our ensemble. We just take mean of all probabilities according to some dimension. Then we can calculate total uncertainty, which is entropy of expected prediction. And this is just sum of minus p multiplied by logarithm of p, where p is expected probability. This is also very simple. And here we can calculate data uncertainty, which is expected entropy of the prediction, and this is just mean of entropies of each predicted distribution for each model in our ensemble. So we take here sum of prob minus prob multiplied by logarithm of prob by some dimension, where prob is prediction of one model in the ensemble. We return all this, and we can calculate knowledge uncertainty as the difference between entropy of expected and expected entropy after we apply this predict uncertainties function. So let's see the predictions of one network, how it works. Here we just evaluate it, and you can see that we have 96% accuracy with it. Using average ensemble prediction, we end up with 97% accuracy, which is slightly better. But this is MNIST, and here I'm showing you only some concepts of what you can use and what you should consider when you apply uncertainty techniques. And afterwards you can check it on more high scale tasks, or look at some repositories where people use some advanced techniques on these tasks, on the high scale tasks, or they use it maybe even on the task of your interest, so which is connected with your work, for example. Okay, here is the code to accumulate all predictions, labels, and uncertainties from our test loader and ensemble. We will not stop here. I turn it to appropriate view here, and that's all predictions is the array with class IDs, where class is class with the highest probability according to ensemble predictions. And errors is the array with ones on the position where our prediction is not true, and 0 are otherwise. So it's just like array with zeros and ones are on the position of wrong prediction. Let's show what we can do with total uncertainty. We can use total uncertainty to understand if in general our predictions are confident. So if we could trust in our model. This is the distribution of total uncertainty. We can see that we have many examples with low total uncertainty and quite few examples with high data uncertainty. But these examples are, and with high probability we have errors in this prediction, in these predictions. Let's check it. Let's calculate cumulative sum of errors in the order of growth of data uncertainty. So we will sort all our predictions in order of growth of total uncertainty. Means that in the beginning of our new sorted array there will be examples with low data uncertainty, low total uncertainty, and in the end we will have examples with a high total uncertainty. And then let's calculate cumulative sum of errors based on this order. We will see, and yes, we can see from this graph, from this figure, that for much examples with for many examples with low total uncertainty, we have 0 error rate. And as our uncertainty grows, then faster and faster we are growing our error rate. So it means that it is true that for cases with high uncertainty we have high probability of error, and we can use this to, for example, use our model in such way that for some threshold, if the prediction is under this threshold, the uncertainty of our prediction is under some threshold, then we will trust our model. And if our uncertainty is above this threshold, then we should not trust it, and we should use either some more complex model, or maybe crowdsourcing system to obtain the result for this prediction. Yes, more about applications of how you can use uncertainty techniques you can find in our video about uncertainty applications. Knowledge uncertainty. Knowledge uncertainty is good because it shows you if there is a lack of knowledge in your predictions. So it is some kind of filter of when you really need to add new data to improve your model, because the example is out of domain if it has high knowledge uncertainty. And and the data uncertainty can also be quite big in out of domain examples, but it is also big when the choice is hard, when you should for example divide some class overlap or something like this. When you have a hard decision, you know that it is hard, you know this data because it is your in-domain data, but you don't know what to choose. Your model doesn't know this. And knowledge uncertainty will not have any growth in this case, because it is focused only on this lack of knowledge and not hard decisions. For out-of-domain data, here I take fashion MNIST. This is a dataset similar to MNIST with some classes where you should choose a class ID for some cloth or shoes. You have images of some clothes, and you should choose appropriate class for it. This is also a calculation of some uncertainty measures and labels on our out-of-domain dataset. And for it, I also have predictions and errors. And you can see that our model is random on this dataset, so it doesn't know true classes because we didn't train it on this dataset, and so it has very low accuracy. And let's look on the distributions of mean likelihood in Ensemble for all classes into datasets. This is just distribution of in general probabilities for some classes into datasets. Means so here we have probability from 0 to 1 of some prediction, and here we have density of these predictions, which plotted with the KDE and Seaborn, and you can see that on our in-domain data we have in general two classes of predictions. We have confident predictions with high probability for some classes that our ensemble understands like true classes. This is predictions of true class for our in-domain data, and we have very low probability for all our classes. So this means that in general in-domain predictions of our ensemble are very sharp. So they have two big maximums. One maximum is with the probability near 1 of the class that our model understands like true class, predicts this class that we should choose this. And we have very low probability for all other classes. And for fashionist, the distribution of probabilities predicted by our model is different. We have the distribution with the maximum nearly near 0.1. So we can say that it is good because this means that in out-of-domain data our ensemble gives quite uniform predictions for all classes. It gives probability 0.1 for each class for 10 classes. Yes, but we also have some variance here, and sometimes our model could be more confident in one class of in-domain data. Let's look on this figure with the distribution, with two distributions of knowledge uncertainty for two datasets, for our in-domain dataset and out-of-domain dataset. You can see that in general we have low knowledge uncertainty in our in-domain data, and we have considerably bigger knowledge uncertainty for our out-of-domain data. And we should use this knowledge to make out-of-domain detection, for example. Yes, for out-of-domain detection you can use any basically any uncertainty that you want, but knowledge uncertainty is the most natural thing to do this, and usually works better on some, I don't know, big images, for example, with high resolution, not here. Because here we can calculate ROC-AUG scores for all three measures of uncertainty, and we see that knowledge uncertainty works worse than data uncertainty or total uncertainty. This could be because some of our fashionist clothes images, they looks very similar to some digits, maybe. And that's why our ensemble gives not very big knowledge uncertainty for these images, for example. But yes, in general, this thing will be bigger than this thing, and knowledge uncertainty is usually works better than data uncertainty for out-of-domain detection. But you should always check it and think of some cases that could work bad. Yes. I also want to mention calibration in this notebook, because it is very important to calibrate your models, especially if they are heavily probabilistic, let's say like that. Okay, what is calibration? We have some true distribution over classes in our dataset, or even in our real world distribution from which we obtain our dataset. This is for example, you can take the array of labels from NIST and calculate probability to meet some class with for example digit 1, and you will end up with some distribution over your classes. So you have classes from 0 to 9 here, and for each class you have some probability in your dataset. And you can also calculate this average probability over your predictions. So you can take your model predictions and calculate how much time how much time you choose this class and this class and so on, or you can just average your probability predictions over all examples in your dataset, and you will end up with some probability distribution over classes that in general gives your model, not not for some particular case, but in general over your dataset. And if these two distributions, real distribution over classes in your dataset and distribution given by your model are different, then you should calibrate your model to make them more closer, because it is not very good for your model and your quality if these distributions are very different. Here we have a good case and our calibration is good. You can see that red number, yes, the red number here is average expected probability over our dataset for our ensemble, and we can see that it is highly correlated with blue, and blue is the real distribution of classes in our test dataset. And it looks quite good, and we shouldn't do some things. We should, let's say, we should not, we can not do anything with this because our calibration is good. But if, for example, this red line with our average predictions will be here and much below the real probability for this class here, and for example much higher than real probability of class here, then we will calibrate our model. For classification it is quite simple with some temperature techniques in softmax or some other approaches that you can find in additional materials in GitHub with this notebook. And for regression it is slightly different, but you also can calibrate your models, and that's it. You should always check your calibration. That's the idea. Okay, now let's move on to deep ensembles for regression. For regression tasks in general, we should consider some other distributions. So for example, here with softmax we can treat it like some categorical distribution and work with it quite easy. For regression tasks, we for example should consider normal distribution, some continuous distributions. But in general, these methods of calculation of total uncertainty, knowledge uncertainty, and data uncertainty are the same, but the formulas are slightly different. By the way, for many distributions, you can find realizations where all statistical methods like entropy, or I don't know, Kullback-Leibler divergence are written inside PyTorch distributions or in some GitHub repositories. So, for example, if we work with the Gaussian ensemble, then with low uncertainty we will have small variance, and all ensembles will predict nearly the same mean. With high data uncertainty we will predict the same mean and slightly and not slightly, we will all models in our ensemble will predict nearly the same mean but high variance. And with knowledge uncertainty we will have some kind of random behavior. We will have different means and different variances, more or less uniformly distributed over some region. I'll use simple toy dataset to show you concepts here, but I will use source files that you can find in our repository with dataset generation and models and optimization classes. I took these sources from our work about regression prior networks, and they are quite flexible and useful, and you can adapt these classes to your work and try them if you want. So our toy dataset is sinus x plus x divided by 10, and also we will add noise to these targets, and noise is big near the zero, so we have only one feature, one real number as a feature, and we have additional noise which is big near the zero and becomes smaller and smaller as you go from zero to left or right. Yes, additional parameters here. We have train limits we have limits for our train data. So x's in train are from -10 to 10. We have out of domain regions from 20 to 25, and from -20 to -25. We have test limits from -15 to 15, which is bigger than train limits. So we could check how our model will behave outside train regions, but not very very far from them. Okay, also we have some trained samples number, test samples number, and so on. We create our loaders of data. So yes, our data looks like that. We have this function. From -10 to 10 we have our train region. Inside 0 we have high noise. This is variance of our targets. You can see that the variance is high nearby 0 and low, and it is becoming lower and lower as we go from 0 to -10 or 10. Yes, and these green points are our in-domain data. Yeah. Here I import some models. Simple model is some model with linear layers and usual ReLU activations, and it during its forward pass it predicts parameters of normal distribution. So mean, the usual output for regression task, and also standard deviation, which we predict with the soft plus activation function. We have also a distribution maximum likelihood estimation trainer and distribution ensemble trainer. This is two classes with methods that are helpful to work with models. They have some train steps, some metrics calculation methods, and so on. You can check it if you are interested. If it is interesting for you, you can check it in the repository. And we also have Gaussian diagonal mixture. This is our class for Gaussian distribution with diagonal matrix with with diagonal covariance matrix. Yes. So we have our model parameters. Input dimension is 1 and output dimension is 1. We have 30 units inside our linear layers and 2 hidden layers. Yes, we create our distribution trainer and train it, and we end up with this image. Blue is real targets, and this orange line is our mean prediction. And you can also see variance plus minus standard deviation for the predictions of single Gaussian model. You can see that in this simple case, Gaussian increases its variance as we go from our train data region. Yeah, and variance looks like this. We have high variance outside -5. So our model doesn't fit well our function, because we had trained data from -10 to -5 also, but its predictions is not very good here in this region. But in generally, our Gaussian model has high variance nearby 0, because we have high noise here, and its variance also grows from 5 to let's say infinity, because it understands that this region is new, and it hasn't got any information about it from training dataset. We can also train an ensemble of Gaussian models. Then the picture will be like this. Here we have also expected variance. This is mean variance over our ensemble. Better say expected. And its behavior is also is quite similar to one Gaussian model on this task. We have high variance nearby 0. It decreases as we go from 0 to -10, and it starts to grow nearby 5. Yeah, you can see that this is our data uncertainty measure. It behaves like that. And we also have knowledge uncertainty measure. And you can see that knowledge uncertainty measure is very low in the noise region. So the noise doesn't increase our knowledge uncertainty here. And it also continues to be quite low even after data uncertainty starts to grow. So we can see that knowledge uncertainty is nearby 0 from -10 to 10 in the whole our train region, and it starts to grow from 10 to the right, or from -10 to the left. And this is a good behavior for knowledge uncertainty. This is what we are expecting. And for out-of-domain predictions, yes, for predictions in our out-of-domain data, we can see that knowledge uncertainty is quite high, much higher than in domain, and thus we can trustfully classify out-of-domain data in this simple case. Okay, let's move on to ensemble distribution distillation. It is usual to distill an ensemble of models into one model in order to save computational time, and in order to save computational time and predictive performance. Yes. Usually in this standard knowledge distillation, data scientists distill an ensemble into one model with the same structure. For example, you can distill an ensemble of Gaussian models into one Gaussian model. and this could work good with in terms of quality of predictions, but this procedure doesn't allow us to calculate uncertainty measures after the distillation, because we can calculate knowledge uncertainty measure only if we have the whole ensemble. And here prior networks and ensemble distribution distillation came, which allows to distill an ensemble of networks into one more general distribution, like distribution over distributions, and calculate uncertainty measures afterwards. For example, for normal distribution, we can consider normal Wishart distributions, and sample from normal Wishart distribution is the parameters of a normal distribution. That's why we can afterwards calculate uncertainty measures based on this prior network, saving computational time, as we will have only one network instead of the whole ensemble. Yes, here I import a distribution ensemble to prior distiller from our source files. You can find these source files in the repo, and I also use normal Wishart prior class. Here we have some parameters of temperature during our distillation. Temperature could be very important, as you know, if we have different local optimas with different models inside our ensemble, it could be hard to put them inside the one model, and temperature allows us to start with quite spreaded distribution, spread mean of our ensemble, and make it more and more sharp as we go further in our optimization procedure. Yeah, we train our distillation and have such an image. This is the figure with predictions of our prior network distilled from our ensemble. And here we have expected variance, data uncertainty measure of our prior network, and you can see that its behavior of this green line is similar to the behavior of data uncertainty inside the ensemble, data uncertainty of our ensemble that we looked on previously. And we have the same behavior of knowledge uncertainty. So here are green points are our out-of-domain examples to somehow show where are in-domain points. And you can see that we have low knowledge uncertainty from -10 to 10. And it starts to grow outside these regions. Well, I think better if we even commit our out-of-domain points. Yeah, it looks like that. So we have knowledge uncertainty that grows outside our trained data regions, and it is quite big in our out-of-domain examples. So this will allow us to calculate good ROCAUC scores for our out-of-domain classification. Yes, so prior networks allow us to distill the whole ensemble with the whole bunch of properties, including uncertainty measures and sometimes improved performance than usual knowledge distillation into the same model as one in the ensemble. Okay, so you can continue this video by playing with this notebook, or you can try to apply uncertainty techniques to your tasks. Find more interesting videos in our track about uncertainty estimation if you are not yet. And this is also the repository of regression prior networks from which I took some code. And thank you for your attention. See you.